Every time a comet appears in the sky, people say the same thing. Wow, look at that. But almost everything you think you know about comets is wrong. Some of them are older than Earth itself. Some are already falling apart before we ever see them. And some don't even belong to our solar system. By the end of this video, you'll understand why comets might be the most important and most dangerous leftovers from the birth of the sun. Let's start with the first mistake most people make. Comets did not form after the planets. They formed before them. When the sun was born about 4.6 billion years ago, it was surrounded by a spinning disk of gas, dust, and ice. Most of that material clumped together to form planets, but not all of it. A huge amount of icy debris was thrown outward by the gravity of Jupiter and Saturn before it ever had the chance to become a planet. That debris was flung into deep space, where temperatures are so low that nothing changes for billions of years. Those leftovers are comets. That's why comets are scientifically priceless. They are time capsules from before Earth existed. Material that never melted, never recycled, never evolved. When we study a comet, we're studying raw solar system history. And here's the second thing most people don't realize. Most comets you hear about have never been near the sun before. They spend almost their entire lives in places like the Oort cloud, a massive invisible shell of icy objects far beyond Pluto. Out there, sunlight is so weak that ice stays frozen indefinitely. So when gravity finally nudges one toward the inner solar system, something dramatic happens. It doesn't arrive, it activates. The moment sunlight hits its surface, frozen gases start turning directly into vapor. That escaping gas drags dust with it, and suddenly a glowing coma and tail appear. The comet didn't turn on, it woke up. Now here's where the classic image completely fails. People call comets dirty snowballs. That's wrong. Spacecraft that have visited comets, like Rosetta, showed us the truth. Comet nuclei are not solid balls of ice. They are fragile, porous rubble piles. Imagine a loosely packed mix of ice, dust, and rock, more like a badly glued pile of debris than a solid object. Some comets are so weakly held together that their gravity barely exists. This matters because it explains something strange. Some comets don't need to hit anything to be destroyed. As they get closer to the sun, sunlight heats the surface, ice turns into gas, pressure builds inside cracks and cavities, entire sections can collapse or peel away. Some comets literally fall apart because of sunlight alone. No explosion, no collision, just heat. And here's a counterintuitive detail. Comet ice can actually be warmer than ice on Earth. Why? Because comets have no atmosphere. When sunlight hits one side, that surface heats up quickly, while the rest stays frozen. That extreme temperature difference causes stress fractures, jets, and sudden outbursts. This is why comets are unpredictable. Two comets with the same orbit can behave completely differently. One brightens smoothly, another suddenly erupts, another quietly disintegrates before anyone notices. That unpredictability isn't chaos. It's physics acting on objects that were never meant to survive heat. And this is just the surface of the story, because once comets start ejecting material, they don't just glow, they change direction, change speed and sometimes rewrite their own fate. And that's where things get really strange, because a comet's tail doesn't just make it beautiful, it turns the comet into something else entirely, a self-propelled object. And in the next section, you'll see how comets can literally push themselves through space, alter their own orbits, and sometimes escape the solar system forever. When a comet gets closer to the sun, something important happens. Ice doesn't melt the way it does on Earth. There's no liquid phase. Instead, frozen gases like water, carbon dioxide, and carbon monoxide turn directly into vapor. This process is called sublimation, and it's violent on a comet scale. That escaping gas doesn't drift away gently, it erupts. Comets develop jets, focused streams of gas and dust blasting out of weak spots in the surface. Space missions have watched these jets turn on and off as the comet rotates, like thrusters firing in deep space. And here's the critical part. Those jets produce force, not much by human standards, but enough to matter when gravity is weak. Comets don't just follow their orbits, they adjust them. Each jet acts like a tiny rocket engine, pushing the comet slightly off course. Over time, those small pushes add up. A comet can arrive earlier or later than predicted. Its path can shift, its rotation can change. This is one reason comet orbits are so hard to predict precisely. They're not passive objects, they're actively reshaping their own motion. Now add rotation. Many comets spin. Some spin slowly, others rotate every few hours. When jets fire unevenly, they can speed that rotation up or slow it down, and that leads to a serious problem. If a comet spins too fast, it can tear itself apart. We've observed this directly. Some comets suddenly fragment without warning, not because of impact, but because rotational stress exceeded what their fragile structure could handle. Others don't break instantly, they weaken. Cracks spread, chunks fall off, material drifts away until a comet loses enough mass that it can no longer hold itself together. This is how comets die quietly. No explosion, no collision, just gradual erosion until nothing remains. And here's something most people never hear. Many meteor showers come from comets that no longer exist. As a comet sheds material along its orbit, it leaves behind a dense trail of dust and debris. When Earth passes through that trail, those particles burn up in our atmosphere as meteors. Every shooting star you see during a meteor shower is a fragment of a comet that may have been falling apart for thousands of years. In other words, we don't just observe comets, we pass through them. And Earth does this regularly. Our planet crosses old comet debris streams every year. Most particles are tiny, grains of sand or smaller, but they survive atmospheric entry surprisingly well. Some of that material has even been found preserved in Antarctic ice, identified by its chemical signature. That means pieces of comets are physically embedded in Earth's environment. Now consider this. Comets lose mass every single time they pass the sun. They don't last forever. Some survive dozens of passes. Others fall apart after just one. Many never make it back out again. A comet's lifespan is limited not by time, but by heat. And this leads to a realization that changes how we think about them. Most comets you see are temporary. They are mid-death. You're not watching a stable object making a visit. You're watching a fragile relic being destroyed in real time. And this destruction doesn't just affect comets. It reshapes the solar system itself. Because the material they lose doesn't vanish. It spreads. It fills space. It becomes part of the environment planets move through. And that leads to an even bigger question. Where do comets actually come from? And how many of them are out there right now waiting to be pushed inward? Because the answer is far more than most people realize. Because beyond the planets lies a region we've never directly seen, a vast reservoir of trillions of comets, so distant, so dark that we only know it exists because comets keep falling out of it. And once you understand where that place is and how unstable it really is, comets stop feeling rare, they start feeling inevitable. To understand comets, you have to stop thinking about the solar system as a flat map of planets. It's not. It's a layered structure, and most of it is invisible. Far beyond Pluto, beyond the Kuiper Belt, far past anything we can directly observe, there's a region that shouldn't exist, but almost certainly does. It's called the Oort cloud. We've never seen it. No telescope has ever captured an image of it, and yet its existence is one of the strongest conclusions in planetary science. Here's why. Long-period comets arrive from every direction, not just from the plane where the planets orbit, but from above, below, and sideways. The only way to explain that distribution is if those comets originate from a spherical shell surrounding the solar system. That shell is the Oort cloud. It's not a neat ring, it's a vast, diffuse swarm of icy objects, likely trillions of them, stretching tens of thousands of times farther from the Sun than Earth is. Some estimates place its outer edge nearly halfway to the nearest star, which leads to a disturbing implication. The Sun's gravity barely holds the Oort cloud together. Out there, the Sun is just one gravitational influence among many. Passing stars, molecular clouds, even the tidal pole of the Milky Way itself can disturb it. And when that happens, comets fall inward. A star doesn't need to come close to Earth to affect us, it only needs to pass close enough to shake the Oort cloud. That disturbance sends showers of comets toward the inner solar system, not immediately, but over millions of years. This means comet activity isn't random. It can be triggered by events happening far beyond our solar system. And that's not the end of it. Some comets don't come from the Oort cloud at all. They come from other stars. In 2017, astronomers detected Oumuamua, the first known interstellar object passing through our solar system. Then came Borisov, clearly a comet from another solar system. These objects weren't captured, they passed straight through, which tells us something unsettling. Interstellar comets must be common. If we detected 2 within just a few years, then the galaxy is likely filled with them, fragments ejected from forming planetary systems, drifting between stars for billions of years. Some of those objects are icy, some behave like comets, and statistically, many pass through our solar system without ever being noticed. This blurs an important line. Not all comets belong to the Sun. Some are visitors from entirely different solar systems, carrying chemistry formed around stars we've never seen. And now connect this back to Earth. If comets are constantly being nudged inward, if the solar system moves through different regions of the galaxy, and if interstellar debris drifts freely between stars, then comet impacts aren't just local accidents, they're part of a galactic process. This helps explain patterns scientists have noticed in Earth's history, periods where impact rates seem higher than average. Those spikes may line up with the Sun's movement through denser regions of the Milky Way. In other words, what happens in deep space doesn't stay in deep space. The galaxy influences comet behavior. Comets influence planets, and planets record the consequences. Which raises the question scientists have been arguing about for decades. Did comets just bring destruction, or did they bring something else? Because once you look inside a comet, chemically, the story takes a very different turn. Because comets don't just carry ice and dust, they carry complex organic molecules, the same kinds of chemistry linked to life itself. And once you understand what's actually inside a comet, the idea that they helped shape Earth stops sounding speculative. It starts sounding inevitable. For a long time, the idea sounded simple. Comets hit early Earth. Comets brought water. Life followed. Then scientists started measuring, and the story got complicated. The first problem was chemistry. Water isn't just water. It carries a fingerprint, a ratio of hydrogen isotopes that tell you where it came from. When researchers measured this ratio in several comets, they found something unexpected. It didn't match Earth's oceans. That result almost killed the idea entirely. If comet water didn't match Earth's water, then comets couldn't be the source, at least not the main one. But then the second wave of data came in. Not all comets are the same. Some comets, especially those that originated closer to the young sun, showed hydrogen ratios that did match Earth's oceans closely. Others didn't. This told scientists something crucial. Earth's water likely came from multiple sources. Asteroids played a role, some comets played a role, and the balance depended on timing, impact frequency, and orbital chaos early in the solar system's history. So comets weren't ruled out, they were narrowed down. But water wasn't the most important discovery. The real shock came when scientists looked at what else comets contained. Space missions and laboratory analysis revealed that comet material is chemically rich, far richer than expected. Inside comet dust, researchers found complex organic molecules, including compounds linked to amino acids. These molecules didn't form on Earth, they formed in cold space, long before planets stabilized. That matters because early Earth was hostile, violent impacts, high radiation, unstable oceans. Life chemistry struggled to survive on the surface. Comets offered something different. They delivered pre-built chemistry. Not life itself, but ingredients already assembled into complex forms, protected inside ice until impact or atmospheric entry released them. This reframed comets completely. They weren't just destructive bodies crashing into planets, they were carriers. Chemical couriers moving material across the solar system and possibly between star systems. And this delivery didn't require massive impact. Small comet fragments, dust grains, and micrometeorites constantly rain down on Earth even today. Many survive atmospheric entry. Some settle gently into oceans, soil, and ice. Over millions of years, that adds up. Earth didn't need one perfect impact. It needed persistence. This also explains something subtle. Life on Earth appeared relatively quickly once conditions stabilized. That rapid emergence may not mean life formed easily. It may mean Earth was already seeded with the chemistry needed to get started. Comets didn't create life, they lowered the barrier. And once you see comets that way, they stop looking like random threats. They start looking like agents of change, which leads to a disturbing balance, because the same objects that deliver chemistry can also erase progress entirely. Comets give, comets take away. And that dual role becomes impossible to ignore when we look at their relationship with planetary extinction. That's where we're going next, because at least one mass extinction on Earth may have had a comet involved. And when you look at how comets interact with giant planets, especially Jupiter, you realize something uncomfortable. The solar system has been rolling the dice for billions of years, and it hasn't stopped. When people think about comet impacts, they usually imagine a single dramatic moment, one object, one collision, one extinction. That image is simple. Reality isn't. Comets don't arrive on neat schedules, and they don't act alone. Their danger comes from patterns, not single events. Early in the solar system's history, planets were still settling into place. Orbits shifted, giant planets migrated, gravity flung debris everywhere. During this period, Earth was hit constantly, not just by asteroids, but by comets thrown inward from distant reservoirs. These impacts shaped the planet's surface, atmosphere, and chemistry. Most of those impacts were small, some were not, and the difference between background damage and global catastrophe often came down to timing. This is where Jupiter enters the story. Jupiter is massive, more massive than all the other planets combined. Its gravity dominates the solar system beyond Mars, and that gravity cuts both ways. Sometimes Jupiter protects Earth. It deflects comets before they ever reach the inner solar system. It captures them. It flings them outward into deep space. But sometimes Jupiter does the opposite. It redirects comets inward. When a comet passes near Jupiter, the planet's gravity can reshape its orbit dramatically, turning a distant object into a short-period comet that crosses Earth's path again and again. This is not hypothetical. We've watched it happen. Comet Shoemaker-Levy 9 didn't just hit Jupiter by accident. It was captured, torn apart by tidal forces, and then slammed into the planet in a spectacular chain of impacts. If Jupiter hadn't been there, fragments of that comet could have been sent inward instead. So Jupiter is not just a shield, it's also a trigger, and Earth's history reflects that balance. There's evidence that comet impacts may have contributed to at least one major extinction event, not necessarily by impact alone, but by environmental disruption. A large comet doesn't need to strike land to cause damage. An ocean impact can inject massive amounts of water vapor and debris into the atmosphere. A near miss can destabilize other objects. A fragmented comet can turn one threat into many. And impacts don't need to be frequent to be effective. They need to be well-timed. This is why extinction appears clustered in Earth's geological record, not because comets strike randomly, but because gravitational dynamics create periods of higher risk. When the solar system passes through denser regions of the galaxy, when stellar flybys disturb distant comet reservoirs, when giant planets subtly shift orbital resonances, impact probability rises, then falls again. Earth survived not because it was safe, it survived because it was lucky, repeatedly. And that luck isn't permanent. Even today, comets remain one of the most dangerous threats to predict. Unlike asteroids, which mostly stay in the same region, long-period comets can appear with little warning, arriving from any direction at extreme speeds. Detection time can be weeks, sometimes less. Which brings us to a quiet truth. The most dangerous comets aren't the famous ones. They're the ones we never see coming. And that danger doesn't come only from impact, because comets can change planets without ever touching them. That's the next layer of the story. Because even a comet that misses Earth completely can still change the planet's climate, atmosphere, and biological trajectory. And once you understand how that works, comets stop feeling like isolated threats. They start feeling like long-term influencers. A comet does not need to collide with Earth to matter. That's one of the biggest misunderstandings about how space actually affects planets. Most of a comet's influence happens before and after any potential impact through material it sheds into space. As a comet approaches the Sun, it releases enormous amounts of dust and gas. That material doesn't vanish. It spreads out along its orbit, forming vast, invisible streams that can stretch millions of kilometers. Earth passes through these streams regularly. When it does, we get meteor showers. That's the visible part. But the majority of the material is too small to burn brightly. Microscopic particles slip into the upper atmosphere quietly, without anyone noticing. Over time, this changes things. Comet dust can alter atmospheric chemistry. It provides surfaces where chemical reactions occur more easily. Some particles absorb sunlight, others reflect it, subtly changing how energy moves through the atmosphere. After large comet breakups, this effect can become significant. A dense dust veil in the upper atmosphere can cool the planet by blocking sunlight. This doesn't require a direct hit. A near miss or a fragmented comet is enough. There's geological evidence that Earth has experienced sudden cooling events that align with periods of increased extraterrestrial dust. These weren't ice ages triggered by plate tectonics, they were atmospheric disruptions. Comets also deliver gases, water vapor, carbon compounds, nitrogen-bearing molecules. All of these can be injected into the upper atmosphere during close passes. Over long timescales, this contributes to atmospheric evolution. This means comets help shape a planet's climate without ever touching its surface. Now scale that up. The inner solar system is not empty space. It's filled with a thin cloud of dust known as zodiacal dust, much of it supplied by comets. Planets move through this material constantly. Earth is sweeping up comet debris every day. Most of it is harmless, but cumulatively it matters. This constant rain of material may have played a role in stabilizing early Earth's atmosphere during critical periods. And then there's another effect most people don't consider: visibility. Comet dust changes how much sunlight reaches the surface. Even small changes in solar input can have outsized effects on ecosystems over long periods. Life responds to gradients. Tiny shifts repeated over millions of years can redirect evolutionary paths. So when we talk about comets as threats, we're missing half the story. They don't just reset planets, they nudge them, slowly, quietly, persistently. And that makes comets far more influential than their rare impacts suggest. But this influence isn't evenly spread. Some comets interact heavily with giant planets before ever reaching the inner system. Others are torn apart long before they get close. And one planet in particular dominates this process more than any other: Jupiter. Because Jupiter doesn't just redirect comets. Sometimes it destroys them. Because Jupiter has quietly torn apart thousands of comets, some of which never reached the inner solar system at all. And in doing so, it has shaped which comets survive long enough to threaten Earth. Next, we'll look at how comets live, age, and die, and why most of them don't last very long at all. Comets are not built to last. That's not a metaphor, it's physics. The moment a comet starts visiting the inner solar system, its lifespan begins ticking down. Every close pass to the sun strips material away, layer by layer, until there's nothing left to hold together. And this process is faster than most people think. Each time a comet swings near the sun, it loses tons of mass. Ice sublimates, dust is blown off, and jets carve new fractures into the surface. Unlike planets or moons, comets don't have strong gravity to hold themselves together. They erode. Some comets survive dozens of passes. Others don't survive one. There are comets that brighten beautifully on approach and then simply vanish. No explosion, no impact. They just fade because the nucleus fragmented into pieces too small to sustain activity. Astronomers call these disappearing comets. We know this because they fail to return on their predicted orbits. Something was there, then it wasn't. In other cases, the death is more dramatic. A comet can split, not because of a collision, but because of internal stress. Uneven heating creates pressure inside weak regions. Rotation stretches the structure. Tidal forces from planets pull it apart. Suddenly, one comet becomes 2, or 10, or hundreds. Each fragment follows roughly the same orbit at first, slowly spreading out over time. This is how some meteor streams are born, not from gentle shedding, but from catastrophic breakup. And here's the key point. Fragmentation doesn't save a comet, it accelerates its death. Smaller pieces lose mass faster, they heat more easily, they disintegrate sooner. What looks like multiplication is actually terminal decay. Eventually, what remains is no longer active. The comet stops producing gas, the tail disappears, what's left is a dark, inert object, chemically altered, depleted of ice. At that point, it's no longer a comet, it becomes something else, an object that looks like an asteroid. This is why the line between comets and asteroids is blurry. Some objects classified as asteroids show sudden comet-like activity. Others move on comet-like orbits but appear dead. These are called extinct or dormant comets. They're the corpses, dark, cracked, covered in an insulating crust of dust that prevents remaining ice from escaping. In fact, many near-Earth asteroids may actually be dead comets, objects that once had tails and jets but burned through their volatile material long ago. This changes how we think about the solar system. Comets aren't rare visitors, they're a phase. Objects transition into comet behavior, then out of it. The solar system recycles them, not into new worlds, but into debris, dust, and asteroid-like remnants. And this means something important. Most comets you'll ever hear about are already dying. You're not watching a pristine object making a brief appearance. You're watching the final stages of something that's been slowly eroding since the solar system formed. Which raises an unsettling question. If comets are constantly being destroyed, why do we still see so many of them? The answer is that they're constantly being replaced. And that replacement mechanism tells us something disturbing about how chaotic the solar system still is. Because for every comet that dies, another one is being nudged inward from far beyond the planets. And the process doing that nudging hasn't stopped. Next, we'll look at why new comets keep arriving, and what that says about the long-term stability of our solar system. If comets are fragile, if they die quickly, then one question matters more than any other. Why do we still see so many? The answer is uncomfortable, because the solar system is not settled. It's still unstable at the edges. Far beyond the planets, in regions like the Kuiper Belt and the Oort cloud, trillions of icy objects remain loosely bound to the sun. These regions are not quiet storage zones. They are gravitational minefields. The sun's gravity out there is weak, very weak. That means even small disturbances matter. A passing star doesn't need to come close to Earth to affect us. It only needs to pass close enough to tug on the outer solar system. That tug slightly reshapes orbits, not dramatically, but enough. And when that happens, some objects fall inward, not immediately, over tens of thousands, sometimes millions of years. This is why new comets appear long after the triggering event. The disturbance sets off a slow cascade. Objects drift inward gradually, one by one, long after the original cause is gone. This means comet appearances are delayed consequences of ancient events. Something happened far away, a long time ago, and only now do we see the result. The Milky Way itself plays a role. As the Sun orbits the galaxy, it passes through regions with different gravitational densities. Molecular clouds, star clusters, and spiral arms all exert subtle tidal forces. Those forces gently stretch and squeeze the Oort cloud. Each pass reshuffles comet orbits. This is why comet influx is not constant over geological time. There are spikes, eras when comets become more common, followed by quieter periods. Earth's impact history reflects this. Clusters of impacts line up with periods when the solar system likely experienced external disturbances. And this process isn't over. The Sun is still moving, stars still pass nearby, the galaxy still pulls. So new comets will continue to arrive, not because something new is happening now, but because something happened long ago. There's another source, too: Jupiter. While Jupiter destroys some comets, it also captures others into short-period orbits. These short-period comets are the ones we see most often, predictable, named, and studied over decades. But they represent only a tiny fraction of the total comet population. Most comets appear once and never return. They either fall apart, get ejected, or swing back into deep space on orbits so long that humanity will never see them again. Which leads to a final realization. Comets are not rare events interrupting an otherwise stable system. They're symptoms. They're evidence that the outer solar system is still slowly unraveling, still responding to forces beyond its control. And if comets are a sign of instability, then studying them isn't just about the past, it's about predicting the future. Because the next question isn't whether new comets will arrive, it's whether we'll see the dangerous ones in time. Because long-period comets don't come from where we're looking. They come from any direction. And that makes them the hardest objects in the solar system to detect before it's too late. If there were a ranking of dangerous space objects, comets would be near the top, not because they're the most destructive, but because they're the hardest to see coming. Asteroids usually stay near the plane of the solar system. We know where to look, their orbits are relatively predictable, and most surveys are designed around that geometry. Comets don't play by those rules. Long-period comets can arrive from any direction, above the solar system, below it, or straight in from deep space. There's no preferred angle, no narrow search zone. That alone makes them difficult. But visibility makes it worse. Far from the Sun, comets are dark, extremely dark. Their surfaces are coated in carbon-rich material that absorbs light instead of reflecting it. Until they warm up, they're almost invisible against the background of space. That means we often don't detect a comet until it's already close, sometimes months away, sometimes weeks, and sometimes less. Detection also depends on brightness, and brightness depends on behavior. Two comets of the same size can behave very differently. One might become active early and brighten gradually. Another might stay dormant until it suddenly erupts. There's no reliable early warning sign. This unpredictability frustrates astronomers because prediction requires consistency, and comets don't offer it. Then there's speed. Long-period comets move fast, very fast. By the time they enter the inner solar system, they're falling inward on steep trajectories, covering enormous distances in short periods of time. That limits response time. And here's another complication most people never hear about. Most comets approach from the direction of the Sun. From Earth's perspective, that's the worst possible angle. The glare of sunlight makes detection extremely difficult. A comet coming from that direction can remain hidden until it swings past the Sun, already deep inside the inner solar system. This is not theoretical. It's happened, which is why some of the most dangerous objects are discovered after they've passed us. Now add one more problem. Surveys are optimized for asteroids, not comets. Comets change shape, brightness, and structure as they approach. Their diffuse comas confuse automated detection systems designed to track point-like objects. Some comets don't look like single objects at all. They look like clouds. Others fragment suddenly, creating multiple targets where there was one. All of this makes tracking difficult. And this leads to a sobering conclusion. The comets we know about are not the comets we should worry about most. The real concern is the population we haven't seen yet. Long-period comets arriving for first-time visits from directions we don't regularly monitor with behavior we can't predict. This doesn't mean impact is imminent, but it does mean uncertainty is built into the system, which is why modern astronomy is trying to change the rules. New surveys are being designed to scan the entire sky more frequently, including regions closer to the Sun. Space-based observatories are being planned specifically to catch inbound objects earlier. But even with better tools, some comets will still slip through. That's not a failure. It's a consequence of scale. And once you understand how many comets exist and how little warning some give, another realization sets in. Comets aren't rare events, they're constant. We just don't notice most of them. Because even when comets are detected, they don't always behave the way we expect. Some brighten dramatically, some fade, some explode. And scientists still can't reliably predict which ones will do what. Next, we'll look at the most unpredictable behavior of all, comet outbursts, and why they still catch astronomers off guard. Sometimes a comet does everything right. It follows its predicted path. It warms gradually. It brightens slowly. And then it doesn't. Without warning, its brightness jumps by a factor of 10, or 100, or even 1,000. These events are called comet outbursts, and for a long time they made no sense. There was no impact, no close planetary paths, no obvious trigger. The comet just changed. The reason lies beneath the surface. Remember, comet nuclei are not solid. They're porous, layered, and full of trapped gases. As sunlight penetrates the surface, it heats subsurface ice unevenly. Pressure builds in pockets and cavities. Eventually, something gives. A crust collapses, a sealed pocket ruptures, a fracture suddenly opens. When that happens, gas escapes violently, dragging dust with it. The coma expands rapidly, reflecting far more sunlight, and the comet appears to explode in brightness. But this isn't an explosion in the usual sense. It's decompression, like popping a pressurized container that's been sealed for billions of years. Some comets do this repeatedly. They flare, fade, then flare again, each time revealing new layers. Others experience a single major outburst and then fall apart shortly afterward. And this behavior is nearly impossible to predict. Two comets with similar sizes and orbits can behave completely differently because their internal structures are different. One may have thick insulating layers, another may be riddled with weak spots. This is why comet forecasts are so unreliable. Astronomers can calculate orbits with extreme precision, but they can't see inside the nucleus. So when a comet suddenly brightens or suddenly disintegrates, it's not because the math was wrong. It's because the object itself changed. There's another twist. Some outbursts aren't driven by water ice at all. Far from the Sun, where water should still be frozen solid, some comets already show activity. That's because they contain more volatile ices, substances like carbon monoxide and carbon dioxide that vaporize at much lower temperatures. These gases can tower jets long before a comet reaches the inner solar system. This means a comet can be active and unpredictable at distances where we don't expect anything to happen. And then there are the rare cases, comets that truly fragment, not gradually, not quietly. They split into multiple pieces, sometimes dozens, sometimes hundreds, spreading out along their orbit. Each fragment becomes a potential source of debris, dust, and meteors. And some famous comets vanish this way, breaking apart completely and never returning. And when that happens, it changes more than the comet's fate. It reshapes the environment planets move through. Which brings us to something counterintuitive. Comets don't just glow. They interact with the sun itself. And that interaction produces something no one expected when it was first discovered. Because comets don't just reflect sunlight, they emit X-rays. And understanding why forced scientists to rethink how the solar wind interacts with the solar system. For a long time, astronomers thought they understood how comets shine. Sunlight hits dust, gas glows. End of story. Then, in the 1990s, something strange happened. Space telescopes started detecting X-rays coming from comets. That made no sense. X-rays usually come from extremely hot, violent environments, exploding stars, black holes, supernova remnants. Comets are cold, fragile objects. They shouldn't be producing X-rays at all. At first, scientists thought the instruments were wrong. They weren't. The X-rays were real. And the explanation forced scientists to look at comets in a completely new way. The key player wasn't the comet, it was the sun. The sun constantly emits a stream of charged particles called the solar wind. This wind flows outward through the solar system at hundreds of kilometers per second, carrying energy and electric charge. Normally, when the solar wind hits a planet with an atmosphere or magnetic field, it creates auroras. But comets don't have atmospheres or magnetic shields. They have something else, a giant cloud of gas. As a comet approaches the sun, it releases neutral gas, mostly water vapor, oxygen, and carbon compounds. And when the high-energy solar wind slams into this cloud, a process called charge exchange occurs. Highly charged solar wind ions steal electrons from the comet's gas. When those electrons snap into place, they release energy. That energy comes out as X-rays. So the comet isn't generating X-rays itself. It's acting like a target, a glowing interaction zone between the sun's energy and ancient material from the edge of the solar system. This discovery was important for two reasons. First, it showed that comets are deeply connected to solar activity. Changes in the solar wind directly affect how comets behave, glow, and evolve. Second, it gave scientists a new way to study the solar wind itself. By watching how comets emit X-rays, researchers can map conditions in space that are otherwise invisible. Comets became probes, natural sensors drifting through the sun's influence. And once again, this blurred a line people thought was clear. Comets aren't passive objects reacting to sunlight. They are active participants in the space environment, constantly exchanging energy with the sun. But this interaction doesn't just produce X-rays. It produces something else, something enormous, something that makes comets look far larger than they actually are. Because a comet's visible glow is only a tiny part of its true size. Its surrounding cloud, the coma, can grow larger than the sun itself. And understanding how that's possible reveals just how deceptive comets really are. When you see a comet in the sky, you're not actually seeing the comet. You're seeing the aftermath of the comet. The solid core, the nucleus, is tiny, often just a few kilometers across. Some are smaller than a city. But surrounding that nucleus is something enormous, the coma. As a comet heats up, gas and dust stream off the surface in all directions, forming a vast cloud around the nucleus. This cloud can grow unbelievably large. In some cases, the coma becomes larger than the Sun. Not brighter, not more massive, just physically wider, millions of kilometers across. That size difference creates a dangerous illusion. People imagine comets as massive objects barreling through space. In reality, most of what we see is empty space filled with gas and dust. The solid part is tiny, fragile, and weakly held together. Which leads to another shocking fact. Comets are some of the least dense objects in the solar system. Measurements from spacecraft show that many comet nuclei are so porous that if you could place one on water, ignoring gravity, it would float. That low density explains why landings are so difficult. When the Rosetta mission tried to land its probe on Comet 67P, it didn't touch down smoothly. It bounced multiple times. The gravity was so weak that anchoring systems failed. That weakness also explains why comets break so easily. Cliffs collapse, overhangs fall, entire sections slough off into space. Images from comet missions show landscapes that look eroded, not by wind or water, but by repeated heating and cooling, by jets undermining the surface from below. Comets crack like drying clay, and those cracks matter. They expose fresh ice. They allow gas to escape more violently. They create feedback loops that accelerate destruction. This is why comets don't age gracefully. Each pass near the Sun roughens them further. Their surfaces darken. Their activity becomes uneven. Eventually, a thick crust forms that traps remaining ice beneath it. At that point, the comet looks dead. But it isn't always. Sometimes that crust breaks, and when it does, dormant comets can suddenly reawaken after years or centuries of inactivity. This unpredictability is what makes comets scientifically valuable and operationally dangerous. You can't tell how active a comet will be just by looking at its orbit. You have to understand its structure, and even then surprises happen. Which brings us to something that quietly complicates everything. Not all objects that look like asteroids are asteroids. Some of them are comets in disguise. Because the boundary between comets and asteroids isn't real. Some objects switch identities, and that confusion matters more than most people realize. For a long time, astronomy treated comets and asteroids as two different things. Asteroids were rocky, comets were icy. End of story. That separation doesn't survive contact with data. As telescopes improved and tracking got better, astronomers started finding objects that didn't fit either category cleanly. Some objects followed comet-like orbits, long, tilted, looping paths, but showed no tails, no gas, no activity. They looked like asteroids. Others looked like asteroids for years and then suddenly developed tails. These are now called active asteroids or main belt comets, and their existence breaks the old definitions. Here's what's really happening. Many objects we call asteroids are actually dead comets. They used to be active. They used to release gas. They used to have tails. But after repeated passes near the Sun, their surface ice was depleted or sealed beneath a thick crust of dust. Without exposed ice, there's nothing to sublimate, so the object appears inert. It doesn't stop being a comet. It just stops advertising the fact. And sometimes that disguise fails. A small fracture opens. A buried pocket of ice gets exposed. Suddenly, gas escapes, and an asteroid grows a tail. This has been observed directly. Objects once cataloged as asteroids have unexpectedly shown comet-like behavior, forcing scientists to reclassify them. The reverse happens too. Some comets lose activity so completely that they become indistinguishable from asteroids except by their orbit. This blurring matters for one reason above all others: risk. Asteroid tracking programs are designed around asteroid behavior, predictable brightness, solid shapes, stable motion. Comet-like objects don't follow those rules. A dormant comet near Earth might look like a harmless asteroid until it suddenly becomes active, changes brightness, sheds material, or fragments. That unpredictability complicates impact assessment. It also complicates our understanding of near-Earth space. A significant fraction of near-Earth objects may actually be extinct or dormant comets, bodies with a very different internal structure than rock-solid asteroids. That means their response to stress, heating, or tidal forces would be different, more likely to fragment, more likely to shed debris, more likely to behave unexpectedly. This also changes how we think about the solar system's history. The boundary between comet and asteroid isn't a wall, it's a gradient. Objects move along it over time, which leads to a deeper realization. Comets aren't a separate population visiting the solar system. They're part of a continuous cycle of transformation. And once you see that cycle clearly, one final question becomes unavoidable. If comets, asteroids, dust, and debris are all connected, then how much comet material is actually out there right now? The answer is more than most people are comfortable with, because comet dust doesn't disappear when a comet dies. It spreads. It fills the inner solar system, and Earth is moving through it constantly. Next, we'll look at how comet debris surrounds us and why it matters more than you think. When we imagine space, we imagine emptiness, black, silent, clean. That picture is wrong. The inner solar system is filled with dust, not thick enough to notice directly, but dense enough to matter. And a large portion of that dust comes from comets. Every time a comet sheds material, it adds to a vast cloud of fine particles spread along planetary orbits. Over time, those particles don't disappear, they accumulate. This is what creates the zodiacal dust cloud, a thin disk of debris stretching through the inner solar system, roughly aligned with the plane of the planets. You've probably seen it without realizing it. Under dark skies, just after sunset or before sunrise, there's a faint triangular glow rising from the horizon. That glow is called zodiacal light. It's the light of our own star reflecting off the debris of destroyed comets. And Earth is moving through this cloud all the time. Our planet sweeps up tons of extraterrestrial material every day. Microscopic grains, too small to see, but large enough to measure. Many of these grains are chemically distinct from asteroid material and match known comet signatures. Some settle into oceans, some into soil, some into ice. This slow accumulation matters because dust behaves differently than rocks. Dust interacts with sunlight more efficiently. It affects how heat moves through space. It influences the thermal balance of the inner solar system in subtle but persistent ways. On large enough scales, dust density changes can affect planetary climates. And there's another effect most people never consider: drag. As dust spreads inward, It slowly spirals toward the sun under the influence of solar radiation. This process, called Poynting-Robertson drag, acts like a slow conveyor belt, constantly reshaping the dust environment around Earth. That means the space Earth moves through today is not the same space it moved through millions of years ago. The solar system's environment evolves quietly, continuously. This also explains why meteor showers fade over time. As dust trails spread out, thin, and disperse, Earth passes through weaker streams. What was once a dramatic celestial event becomes a minor one. Comets don't just create momentary spectacles, they leave long-term fingerprints on space itself. And those fingerprints extend far beyond Earth. Dust affects how sunlight heats planets. It influences atmospheric chemistry. It shapes the interplanetary environment that spacecraft travel through. In a very real sense, we don't live in empty space. We live inside the remains of comets, which leads to a final uncomfortable realization. If dust from destroyed comets fills the inner solar system, then what we call normal space is actually the aftermath of billions of years of comet death. And that forces one last question. Are comets just remnants of the past, or are they still shaping the future? Because comets don't just affect planets. They help explain how planetary systems form, migrate, and sometimes fail, even around other stars. Next, we'll step outside the solar system and see what comets tell us about planetary systems across the galaxy. For a long time, comets felt like a local problem, something that belonged to our solar system alone. That idea didn't survive the discovery of other stars with planets. Once astronomers began studying exoplanet systems, they noticed something familiar and unsettling. Dust. Around many stars, telescopes detect massive debris disks, clouds of dust and ice far denser than anything around our sun today. These disks glow in infrared light, revealing constant collisions and ongoing destruction. The only way to maintain that much dust is replenishment, which means those systems are actively producing comet-like objects. In some cases, we're seeing the equivalent of young Oort clouds in formation, reservoirs of icy debris being scattered outward by giant planets, just like Jupiter and Saturn did here. This tells us something critical. Comets are not an accident. They are a natural byproduct of planetary formation. Whenever giant planets form and migrate, they destabilize smaller icy bodies. Those bodies get flung outward, trapped in distant reservoirs, or sent plunging inward toward the star. That process appears to be common, which also means comet bombardment is common. Young planetary systems often go through violent phases where comets rain inward repeatedly, reshaping surfaces, atmospheres, and chemistry. This reframes Earth's early history. The chaos we went through wasn't unusual, it was expected. Some exoplanet systems show signs of ongoing comet activity even billions of years after formation. Others appear unusually quiet, suggesting different planetary architectures lead to very different comet dynamics. And this is where comets become diagnostic tools. By studying dust and debris around other stars, astronomers can infer the presence of unseen planets. The structure of the dust reveals where massive bodies must be shaping orbits. In other words, comets help us detect planets we can't see directly. They also help explain why some exoplanets have thick atmospheres, and others are stripped bare. Heavy comet bombardment can deliver volatiles, water, carbon compounds, nitrogen, building atmospheres over time. Too much bombardment or badly timed impact can do the opposite. Comets giveth, comets taketh. And this balance appears everywhere we look. Even more intriguing is the implication for life. If comets delivered key chemistry to Earth, then similar processes may be happening, or may have happened, elsewhere. Not because life is inevitable, but because the ingredients are widely distributed. Interstellar comets make this even more likely. Objects ejected from one system can pass through another, carrying chemistry across stellar boundaries. That means planetary systems are not chemically isolated. The galaxy mixes, slowly, imperfectly, but persistently. And this brings us to the final perspective. Comets aren't just leftovers from formation. They're messengers, carrying information about how systems form, evolve, and sometimes fail. Which means studying comets isn't about nostalgia for the past. It's about understanding the rules that still govern planetary systems today. And those rules have consequences, because the same processes shaping distant systems are still operating here, right now. Because comets didn't finish their role billions of years ago. They're still arriving, still breaking apart, still interacting with planets. And the final question isn't whether comets matter, it's whether we're prepared for the next chapter of their influence. Comets were not a closed chapter. They didn't finish their work billions of years ago, and they're not just relics drifting harmlessly through space. They're still arriving, still breaking apart, still reshaping the environment Earth moves through. The only difference now is awareness. For most of human history, comets appeared without warning. They showed up suddenly, vanished just as fast, and left behind fear, myths, and guesses. Today, we understand far more, but not enough. Long-period comets can arrive from any direction, moving fast, dark, and unpredictable. Some will be detected early, others won't. That's not pessimism, it's geometry and physics. And impacts are only part of the risk. Comets influence climate without hitting. They deliver material without colliding. They change planetary environments quietly over time. They are a slow variable in a system that prefers stability. That's why comets remain one of humanity's biggest blind spots in planetary defense. Not because they're common threats, but because they're rare, sudden, and hard to predict. And yet comets are also the reason Earth is the way it is. They helped shape our oceans. They enriched our chemistry. They may have accelerated the conditions that allowed life to begin. The same objects capable of resetting a planet may have helped build it in the first place. That contradiction isn't a flaw in the story. It is the story. Comets remind us that planetary systems aren't clean, orderly machines. They're messy, chaotic, influenced by forces far beyond the planets themselves. The solar system is not finished evolving. Neither is the galaxy around it. And Earth exists in the middle of that process, not protected, not doomed, but participating. So when you see a comet streak across the sky, you're not watching a visitor. You're watching a fragment of ancient history interacting with the present. A reminder that the space we live in is active, connected, and still shaping what comes next. Comets don't arrive to announce the end. They arrive to remind us that nothing here was ever guaranteed. And that understanding, not fear, is what finally gives us perspective. The universe doesn't erase its past. It keeps sending pieces of it back. If this changed how you see comets, tap like. Subscribe if you want more real space science. No hype, no myths, just how the universe actually works. And I'm curious, what surprised you the most? The danger, the chemistry, or how common comets really are? Drop that in the comments. More is coming. If this surprised you, like the video. Subscribe for more real space science. And comment, what about comets fascinates you most? See you again. Bye. The solar system's environment evolves quietly, continuously. This also explains why meteor showers fade over time. As dust trails spread out, thin, and disperse, Earth passes through weaker streams. What was once a dramatic celestial event becomes a minor one. Comets don't just create momentary spectacles, they leave long-term fingerprints on space itself. And those fingerprints extend far beyond Earth. Dust affects how sunlight heats planets. It influences atmospheric chemistry. It shapes the interplanetary environment that spacecraft travel through. In a very real sense, we don't live in empty space. We live inside the remains of comets. Which leads to a final uncomfortable realization. If dust from destroyed comets fills the inner solar system, then what we call normal space is actually the aftermath of billions of years of comet death. And that forces one last question. Are comets just remnants of the past, or are they still shaping the future? Because comets don't just affect planets. They help explain how planetary systems form, migrate, and sometimes fail, even around other stars. Next, we'll step outside the solar system and see what comets tell us about planetary systems across the galaxy. For a long time, comets felt like a local problem, something that belonged to our solar system alone. That idea didn't survive the discovery of other stars with planets. Once astronomers began studying exoplanet systems, they noticed something familiar and unsettling. Dust. Around many stars, telescopes detect massive debris disks, clouds of dust and ice far denser than anything around our sun today. These disks glow in infrared light, revealing constant collisions and ongoing destruction. The only way to maintain that much dust is replenishment, which means those systems are actively producing comet-like objects. In some cases, we're seeing the equivalent of young Oort clouds in formation, reservoirs of icy debris being scattered outward by giant planets, just like Jupiter and Saturn did here. This tells us something critical. Comets are not an accident. They are a natural byproduct of planetary formation. Whenever giant planets form and migrate, they destabilize smaller icy bodies. Those bodies get flung outward, trapped in distant reservoirs, or sent plunging inward toward the star. That process appears to be common, which also means comet bombardment is common. Young planetary systems often go through violent phases where comets rain inward repeatedly, reshaping surfaces, atmospheres, and chemistry. This reframes Earth's early history. The chaos we went through wasn't unusual, it was expected. Some exoplanet systems show signs of ongoing comet activity even billions of years after formation. Others appear unusually quiet, suggesting different planetary architectures lead to very different comet dynamics. And this is where comets become diagnostic tools. By studying dust and debris around other stars, astronomers can infer the presence of unseen planets. The structure of the dust reveals where massive bodies must be shaping orbits. In other words, comets help us detect planets we can't see directly. They also help explain why some exoplanets have thick atmospheres, and others are stripped bare. Heavy comet bombardment can deliver volatiles, water, carbon compounds, nitrogen, building atmospheres over time. Too much bombardment or badly timed impact can do the opposite. Comets giveth, comets taketh. And this balance appears everywhere we look. Even more intriguing is the implication for life. If comets delivered key chemistry to Earth, then similar processes may be happening, or may have happened, elsewhere. Not because life is inevitable, but because the ingredients are widely distributed. Interstellar comets make this even more likely. Objects ejected from one system can pass through another, carrying chemistry across stellar boundaries. That means planetary systems are not chemically isolated. The galaxy mixes, slowly, imperfectly, but persistently. And this brings us to the final perspective. Comets aren't just leftovers from formation. They're messengers, carrying information about how systems form, evolve, and sometimes fail. Which means studying comets isn't about nostalgia for the past. It's about understanding the rules that still govern planetary systems today. And those rules have consequences, because the same processes shaping distant systems are still operating here, right now. Because comets didn't finish their role billions of years ago. They're still arriving, still breaking apart, still interacting with planets. And the final question isn't whether comets matter, it's whether we're prepared for the next chapter of their influence. Comets are not a closed chapter. They didn't finish their work billions of years ago, and they're not just relics drifting harmlessly through space. They're still arriving, still breaking apart, still reshaping the environment Earth moves through. The only difference now is awareness. For most of human history, comets appeared without warning. They showed up suddenly, vanished just as fast, and left behind fear, myths, and guesses. Today, we understand far more, but not enough. Long-period comets can arrive from any direction, moving fast, dark, and unpredictable. Some will be detected early, others won't. That's not pessimism, it's geometry and physics. And impacts are only part of the risk. Comets influence climate without hitting. They deliver material without colliding. They change planetary environments quietly over time. They are a slow variable in a system that prefers stability. That's why comets remain one of humanity's biggest blind spots in planetary defense. Not because they're common threats, but because they're rare, sudden, and hard to predict. And yet, comets are also the reason Earth is the way it is. They helped shape our oceans. They enriched our chemistry. They may have accelerated the conditions that allowed life to begin. The same objects capable of resetting a planet may have helped build it in the first place. That contradiction isn't a flaw in the story. It is the story. Comets remind us that planetary systems aren't clean, orderly machines. They're messy, chaotic, influenced by forces far beyond the planets themselves. The solar system is not finished evolving. Neither is the galaxy around it. And Earth exists in the middle of that process, not protected, not doomed, but participating. So when you see a comet streak across the sky, you're not watching a visitor. You're watching a fragment of ancient history interacting with the present. A reminder that the space we live in is active, connected, and still shaping what comes next. Comets don't arrive to announce the end. They arrive to remind us that nothing here was ever guaranteed. And that understanding, not fear, is what finally gives us perspective. The universe doesn't erase its past. It keeps sending pieces of it back. If this changed how you see comets, tap like. Subscribe if you want more real space science. No hype, no myths, just how the universe actually works. And I'm curious, what surprised you the most? The danger, the chemistry, or how common comets really are? Drop that in the comments. More is coming. If this surprised you, like the video. Subscribe for more real space science. And comment, what about comets fascinates you most? See you again. Bye.